Hello and welcome. In a previous lecture, we talked a bit about how the central limit theorem tells us that the sampling distribution of sample means will be approximately normally distributed if the samples that we're drawing are sufficiently large. In this lecture, we're going to talk a little bit more about that sufficiently large sample size requirement and particularly why it is so important for skewed distributions. We're going to be looking at some example data about how many basketball games in a season Duke students attended. So this is capped at around 30, which is the number of basketball games in the NCAA season, and this histogram shows us how many games Duke students attended. So the bulk of students attended between 0 and 10 games. Some students attended between 10 and 20, and very few students attended between 20 and 30 games. The central limit theorem tells us that the distribution of sample means, so means of samples that we draw from this population, are going to be approximately normally distributed if the sample sizes that we draw are large enough. So let's take a look at a couple of examples of these sampling distributions of sample means for different sample sizes. So here is an example where we've taken samples of size 10 from the population data and then calculated the mean of that sample, done that over and over and over again, and plotted the distribution. And you can see here that this distribution is still pretty right skewed, just like the population distribution that it came from. Take a minute and see if you can answer the following questions about what this data is telling us. So what does each observation in the distribution represent? And is the variability of this sampling distribution going to be smaller or larger than the variability of the distribution in the population? So each observation in the distribution is a sample mean of a sample of size 10, and sample means are going to vary less than individual observations when they're plotted out, so the variability of this sampling distribution is smaller than the variability of the population distribution. Taking a mean of a sample collapses variability down toward one central value, and then when we plot those distributions out, the variability of those means is going to be smaller. Here's another example, except for in this case, instead of taking samples of size 10, we've taken samples of size 30. So we've taken samples with n equals 30 from the population distribution, we've calculated the means of each of those samples, and we have plotted them out in this histogram. So how did the shape of this distribution, the center of the distribution, and the spread or the variability of the distribution change when we made this change from n equals 10 to n equals 30? Well, the center of the distribution stays about the same, which is what we expect. This distribution of sample means should stay approximately centered on the mean of the population. But the shape of the distribution becomes more normal, which is what the central limit theorem tells us should happen. When we take larger and larger samples, what we should get is a more and more normally distributed distribution of sample means. The spread of the distribution, the variability of the distribution, is smaller. This is because when we take the means of larger and larger samples, those means are going to be closer and closer to the true population mean. Those samples are going to tend to be more representative, they're going to be less sensitive to extreme values, and so when we take a larger sample and then take the mean of those samples, the mean is going to be less likely to vary extremely from the actual population mean, and so when we plot out the distribution, there's not going to be a lot of more extreme observations, and so the distribution overall is not going to vary as much. The same principles hold when we up our sample size again, so that we're taking samples of size 70 from the population, calculating those sample means and plotting them out. So again, here the distribution has become more normal, the center of the distribution is about the same, and the variability has gotten even smaller because we've been taking even larger samples. So even though we were drawing from an extremely right-skewed distribution, where almost all of our observations were in that first bar of the histogram between 0 and 10, when we take large enough samples, samples of even size 70, what we are going to end up with is a sampling distribution of sample means that is approximately normal, just like the central limit theorem says should happen. So here's a practice question about how we could use a sample drawn from this population data, analyze that sample to give us an estimate of the real population average number of games that these students attended per season. So if the mean of the sampling distribution is 5.75 and the standard deviation of the sampling distribution, or the sampling error, is 0.75, how would we calculate the 95% confidence interval around our estimate of the average number of games attended by students? So remember that our formula for the 95% confidence interval is our point estimate. So in this case, the mean of the sampling distribution, 5.75, plus or minus a critical value times a standard error. So our critical value is approximately 2 for a 95% confidence interval, and our standard error is 0.75. So the correct answer here is B, our point estimate, 5.75, plus or minus 2 times the standard error. And to wrap up, here is one more problem where you can test yourself to see if these concepts regarding the size of a sample and the central limit theorem have really hit home. In this skewed population distribution with a mean of 10 and a standard deviation of 7, look at these plots of data drawn from this population distribution and see if you can match up the descriptions in this left-hand column to the plots in the right-hand column. So the first of these descriptions is a single random sample of 100 observations from the population. Because it's a random sample and because the size of the sample is sufficiently large, what we're looking for is a distribution of these sample values that basically has the same shape as the population distribution. So in this case, that's plot B. The second description is a distribution of 100 sample means from random samples of size 7, so pretty small samples that we've calculated sample means for and plotted the means. So in this case, that's plot A. This is a distribution of sample means that's still pretty right skewed. It doesn't look very normal, and that's because the samples that we are drawing are pretty small. The final description is a distribution of 100 sample means from random samples with size 49. So in this case, pretty decent sized random samples. And that's going to be associated with plot C. This is a distribution of sample means that is more or less normal. And that's because the samples that we are drawing from the population are of a decent enough size that the central limit theorem is really going to kick in, and we're going to get this distribution of sample means that is more or less normal. So that's been our continued discussion of the importance of sample sizes for the central limit theorem and statistical inference. Thank you for listening, and I will see you next time.